Welcome to association rules part 2. So, as we had discussed, what we want to do is to find out all association rules of the form x arrow y, where x is an item set and y is an item set, such that the support and confidence criteria are satisfied. Support and confidence criteria are satisfied. So, we have defined support to be the number of transactions where the union x and y appear, and confidence to be the fraction of transactions where y appear as well as x appear divided by number of transactions where only x appear. If both these ratios are greater than some preset threshold, mean sup and mean comp, we call it to be a association rule. And we found that if we try to discover such rules, finding all possible combination is computationally prohibitive. So, then we adopt a two-step approach. The first approach is find out all item sets, all sets of item whose support is greater than min sup, and for each of these item sets we divide them into two parts, two sets of item, one in the left, one in the right, and then for each of these partitions we check the confidence. If it is greater than the confidence threshold, we select it. So, there are two steps. First is finding frequent item set, second is doing the rule generation from the identified frequent item sets. So, but still this finding frequent item set is computationally expensive, because let us see why it is computationally expensive. So, suppose I have 5 items in a store, for example. Let me denote them as A, B, C, D and E. Beer, Coke, diaper, bread, milk, A through E, 5 items. So, I can form an item set of size 5 item set. You remember the definition of K item set, 5 item sizes 5. So, all A, B, C, D, one such 5 item sets are there. There are 4 possible 4 item sets containing 4 elements, A, B, C, D, A, B, C, A, B, D and so on. There are 10 possible 3 item sets, A, B, C, A, B, D and so on. So, basically what we are doing is that, see, a person, suppose there are 5 items available for sale in the store, a customer can buy any of these combinations. A customer can buy all 5 items, a customer can buy 4 out of these 5 items, a customer can buy 3 out of these 5 items, 2 out of these 5 items and so on. So, all these ellipses, white ellipses shows that and then finally, a null, the customer might not buy anything. So, this lattice sort of tells us that all the possible item sets that might be present in a market basket, we call them as candidate item sets, any choice of purchases. So, if there are d possible items, you can easily check that there are 2 to the power d possible item sets possible, exponential 2 to the power d possible item sets possible. Okay. So, either one item set is present or absent in a bag. So, 5 are there, so d are there, so 2 to the power d. Not only that, you see that these item sets, you can sort of arrange them in a lattice like structure. Okay. So, in the top of the lattice is no item set, bottom of the lattice is a 5 item set or k item set, and then at each level of the lattice there are k, k minus 1, k minus 2 and so on. So, 4 item sets, 3 item sets, 2 item sets, 1 item sets and so on. And then I can also draw a line connecting these individual levels, saying that if one is a subset of the other. For example, the set ABCD, 4 item set ABCD can produce 4 different subsets of size 3, ABC, ABD, ACD, BCD. Okay. So, if I look at this, there are there are this will produce this, right, just a minute. So, there are this ABCD, it will produce ABC as a sub. So, I draw this line if say this, if this is a subset of this, then I draw a line. Okay. So, for example, ABC is a subset of ABCD, ABD is a subset of ABCD and so on. So, if I arrange these 2 to the power d subsets, I can sort of draw this kind of a lattice, saying that which is a subset of which is a subset of which. If you carefully see this diagram, you will see that these lines are nothing but one is a subset of, and this can go across all levels. For example, this ABC is subset are AB, AC and BC, AB is a subset of AB subsets are A and B and so on. Okay. So, the thing to be noted is that this lattice represents all possible candidate item sets that one may think of. Okay. Now, tell me how do I find, so my first job is to find out what are the frequent item sets. So, how I do that? First I set a support threshold, you know frequent means number of times is more than the support. I set a support threshold, maybe I set a support threshold that it is 10% of the total number of transactions. So, if the total number of transaction is 100, a particular item set should appear more than 10 times, it should appear. Okay. So, what I will do to find out what are if that is so, then I call it as a frequent item set. So, how do I do it? So, I will take any of this, for example, I will take ABCD, I will go through these 100 transactions and see whether each of them contains ABCD or does not contain ABCD. I will scan this entire 100 transactions, find out if it contains ABCD or does not, and then I will count how many of these 100 are containing ABCD. If that number is greater than this 10% of the total, then I will say ABCD is a frequent item set. I will say ABCD is a frequent item set, right. So, to among these all possibilities of different item sets, if by brute force I want to find out who among them are frequent, each and every one of these, for each and every one of these I will scan the set of transactions, 100 transactions, in fact there will be millions, 100 transactions. I will check how many times they appear, I will check if they cross the threshold, and I will find out who among them, not all, some of them among these candidates, all these are candidates, are indeed frequent, that means they appear more than min sub number of times. Okay. So, what is the complexity of this? If the total number of item sets possible are m, which in this case is 2 to the power d, and total number of elements in the in the database, that is number of transactions is n, and the average length of each w, because I have to match this string, is w, then it is n into m into w, which since m is a large number 2 to the power d, n is also large. So, this indeed will be very high. Okay. So, now the thing is that, so but how can we reduce this time? Let me give you an intuition. The intuition is that, do I really need to check each and every of these possible candidate item sets to check if they are if they are satisfying the support condition, or if I know somehow that one of these is not frequent, one of this is not frequent, can that help me to figure out whether these subsets of that will be frequent or not frequent? So, in other words, if I know this to be a frequent item set, they appear large number of time, can I say anything about this thing? Let me tell this in plain English. The English is, if I know that people do not buy say milk and bread a lot of time, people do not buy milk and bread a lot of time, that means the set milk and bread is not frequent. Can I say, what can I say about will people buy milk and bread and sugar frequently? So, if I already know that people do not buy milk and sugar frequently, or let me give another example, if I already know people do not buy cricket bat and cricket ball frequently, I can automatically infer that people definitely do not buy cricket bat, cricket ball and cricket gloves not frequently. So, in other words, if cricket bat and ball is not a frequent item set, cricket bat and ball and gloves is definitely not a frequent item set. Okay, is definitely not. That means, I will explain soon why it is so. That means, if ABC I know not to be a frequent item set, I know ABCD is definitely not a frequent item set. Okay. So, let me state this more clearly. I can use this. So, this principle is known as the Apriori principle. Okay. What this principle says is that, is actually another way of putting what I said. If some item set is frequent, then its subsets should also be frequent. Okay. And a way of stating this is, if people buy milk and bread a lot of time, definitely it is obvious that people also buy milk a lot of time, only milk a lot of time. Okay. So, it says that if x is a subset of y, the support of x is definitely going to be more than the support of y. Okay, is definitely going to be more than the support of y. In other words, the support of an item set never exceeds the support of its subset. Let me again explain this with an example. Suppose I consider this set, or let me take this set. sorry, let me consider this set. Suppose I consider the item set bread and milk and diaper, bread and milk and diaper. How many times it appears? It appears 3 times. No, 3 times, 2 times. Bread and milk and diaper appears 2 times. So, one time here and one time here. The set bread and milk and diaper. Okay. Now, so 2 times it appears, the support is 2. Now, you take a subset of these 3, say only bread and milk, only bread and milk, one subset. So, how many times it appear? Definitely it should appear either 2 times or more than 2 times. Okay. In this case, it appears 3 times, bread and milk only. Okay. So, take another subset, take the set bread and diaper, bread and diaper. So, how many times it appears? It appears 3 times. Okay. So, this actually is in agreement with this property, that if X is a subset of Y, a smaller set, its support should be greater than the support I. That means, smaller item sets, subset item sets have more support than their supersets. Okay. So, this is actually known as the anti-monotone property, anti-monotone property of the support function. So, you can directly obtain the a priori principle from this anti-monotone property. It is an obvious extension that it naturally means that if we apply some threshold, if an item set is frequent, its subsets must also be frequent. Okay. So, this property actually helps us avoid evaluating the frequency of all these possible candidate item sets. Why? Because I have already said that if a item set is frequent, all its subsets should be frequent. Other way around, if some item set is not frequent, none of its supersets can be frequent. So, basically if AB is frequent, not frequent, sorry, AB is not frequent, ABC cannot be frequent, ABD cannot be frequent, ABE cannot be frequent. If ABC is not frequent, ABCD cannot be frequent, ABCE cannot be frequent. If ABCD is not frequent, ABCDE cannot be frequent. That means, knowing that this particular set of items AB is not frequent can immediately infer that none of these can be frequent. Okay. None of this can be frequent. So, how this helps? This helps in candidate item set pruning. Earlier, everybody was a candidate for being a frequent item set. Okay. Now, moment I examine one, I can remove this from my candidate set. I need to examine only this. Again, I will examine some of them. If they are found to be infrequent, their entire parent set will be pruned. Okay. So, that is the principle entire. So, here I illustrate it with an example. Suppose there are these 6 items: bread, coke, milk, beer, diaper, eggs, and these are their counts. Okay. And since there are 6 items, all possible combination is 41. If I set some support threshold to be greater than 2, that is 3 and above, then only 13 of these 41 are frequent. Instead of evaluating all these 41, what I can do is that I can remove this coke and egg from further considerations, take only bread, milk and diaper, find out 2 item sets combining milk, bread, milk, beer, diaper only, find their count, find 2 of them are infrequent, take only this other and get ones of size 3 and so on. Okay. So, this way I can proceed. So, this forms the basis of the frequent item set finding algorithm known as the Apriori algorithm. Okay. How does the algorithm proceed? You first generate frequent item sets of length 1, okay, 1 item sets. Find out how many of them are frequent. Okay. So, if we look at this picture, what I do, first I individually find out A, B, C, D, E, which of these are frequent as a single item, and mark only those which are frequent, prune out the remaining lattice. Among the ones that stay frequent, I find out all their combinations in the next level, 2 item set level. Okay. So, I check which of them are frequent by counting, and then if somebody is non frequent, they are further subtree I edit, I prune, and then I go on till I exhaust, go till the bottom, and then I will find out. So, the steps are this: generate item sets of length n, length 1, and then recursively from frequent item sets of length k from item sets of length k plus 1. Why? How? You can see that if I know which are 2 item sets or which are frequent, from that I find 3 item sets which are frequent, k, k plus 1. Okay. Of course, to find out whether they are frequent or not, you have to scan the entire database of transactions, count and do it. So, of course, these are the factors which will still affect your complexity, how many, what is the support threshold, basically how much pruning you can do, number of items in each transaction, size of the database, n, transaction width. So, all this will affect, but still what will happen is that you no longer evaluate all these 2 to the power d item sets. Okay. Many of them will be pruned in this process. Many of them will be pruned in this process. Okay. So, let me quickly give an example of how this proceeds. So, you can actually visualize it with this example. So, if we consider 6 item sets, so so many different combinations are possible, and suppose I set my for the first item set I count what is the support, apply the threshold, find out frequent one item set. From the one item sets, I note that this in the two item sets, this ruled out black ones which are infrequent co-candidate, they do not appear. Only the remaining ones I combine. I combine to get these two item sets. Note that I have to again count for these two. It is not that from this count I can find out this count. I have to again count here, go through the database and count and find out which are frequent, and again from that I find the 3 item sets. Okay. So, this way I proceed. This will go on till either you find the entire number of item sets or no new at the lattice is pruned, no new candidates remain. Okay. Alright. So, this definitely reduces the complexity, and this is applied in large databases. In the next class, we will see, after finding out the frequent item sets, how I will form rules from them using a similar a priori like framework. And we will see from the rules how we can evaluate them and do them. There are many other algorithms which further reduce the complexity, like FP tree, frequent pattern tree. We will discuss them in the subsequent lectures. Thank you for today.